Welcome students for today's DSS lecture. So we will design the beam today. So in the earlier lecture we have discussed and solved a numerical which was an analytical numerical wherein the section was given and we have just calculated the load and done the checks to check whether they are safe or no. So today we will design a beam. So I have taken this numerical example for today's lecture. The question goes like this: design a beam of effective span 6 meters subjected to a UDL of 10 kilonewton per meter along with a 100 kilonewton load. The beam is laterally supported. The thickness of the wall is 230 mm. So this is the given question. So let us check what all is the given data. So first I will write given data. So given data. So span is given. Span is 6 meters. Then load is given. Load we have UDL of 10 kilonewton per meter and a point load of 100 kilonewton. Now if they are not specified any location, then the point load is to be taken at the center. Then the beam is laterally supported throughout. Now the thickness of the wall is 230 mm. The meaning of this is that beam is resting on the wall like this. This is a beam which rests over the wall. So this wall thickness is nothing but this one, 230 mm. So this is nothing but the bearing length. So I will write here bearing length. As per our codebook notation, it is B1, which is 230 mm. We will take it as it is resting over the full wall, that is full bearing is taken into consideration. So let us start solving. However, you know all the steps remains the same. Only the thing is the section is to be chosen by us. Rest all everything will remain the same. So let us start. So the first step is load calculation. Load calculation. So what all we have load. So UDL on the beam is 10 kilonewton per meter. Then we have, so this is UDL. So first I will do the calculation for UDL and I will assume, because we don't know what is the section, we don't know its weight, so I will initially assume it the self weight of the beam. So self weight of beam, I will assume it as 1 kilonewton per meter. So I will write here assumed. So the total UDL will be 11 kilonewton meter. Now in the question we just don't have the UDL, but we also have a point load. So first I will calculate the ultimate load for this. So ultimate UDL load is 11 into 1.5. So just check how much this works out to be. So this works out to be 16.5 kilonewton per meter. Then we have a point load also here. So I will calculate ultimate point load. So we have a point load which is 100 kilonewton, so multiplied by 1.5, so 150 kilonewton is the ultimate load. So I will just draw a diagram of the beam. So this is a beam of span 6 meters we have a UDL on it, which is this 16.5 kilonewton per meter, and a 150 kilonewton point load is acting over here. So we have both the combinations now. We have UDL as well as the point load. So let us calculate the shear force and the bending moment. So maximum bending moment MU. So this will be, for UDL I'll write it separate. So W U L square by 8 plus W L by 4. This is for UDL, this is for point load. So for UDL, WU is 16.5 into 6 square divided by 8 plus this is for point load. So 150 into 6 divided by 4. Now let us check how much this works out to be. So this works out to be 299.25 kilonewton meter. Similarly, we will also calculate maximum shear force, which is VU. So for UDL it will be WUL by 2 plus for point load it will be WU by 2. So WU is 16.5 into 6 divided by 2 plus 150 divided by 2. So let us check how much this works out. So this works out to be 124.5 kilonewton. So we have computed the maximum bending moment and maximum shear force. So now the next step is we should know what is the section, because we don't have the section. So to compute the section, what we have to do is we have to assume a section. So for assume a section, we have to compute with the plastic section modulus. For that, what we'll do is we will go to the clause and we will use the formula for the bending strength. So how do we get the bending strength? It is on page number 53. So on page number 53, we already know that for VU less than 0.6 VD, the bending strength MD is given by beta B ZP Fy divided by gamma M naught. We will make use of this and we will calculate ZP, so that we can take up a section. So the next step is to calculate plastic modulus required. So what we'll do, this we will take according to the clause that is given on page number 53. So the clause is this one, 8.2.1.2, page 53 of IS 800 2007. So we will make use of this formula here. MD is equal to beta B ZP Fy divided by gamma M naught. So I will write the formula. So MD is equal to beta B ZP Fy divided by gamma M naught. Now we are going to calculate ZP here. So ZP will be, so this will come here. So it will be MD into gamma M naught divided by beta B into Fy. Now we will assume here, assuming the section to be plastic, so beta B will become 1, and this MD we will substitute the calculated value of mu, so which is 299.25. so I will just make a changes here. So I will substitute as mu into gamma m naught. We are assuming section to be plastic, so 1 into Fi, because beta B is 1. Now we will substitute and get the value for Zp. So let us check. So mu is how much? Mu is, we have calculated 299.25. so it is 299.25 into 10 raised to 6 into gamma m naught is 1.1. Beta B we assumed it as 1 and Fy is 250. So let us check how much we get. So we are getting it like this, 1.3167 into 10 raised to 6 mm cube. So I will convert it into centimeter cube, because in our steel table and in our IS 800 the Zp value will be given in terms of centimeter cube. So I will write it. So this will be 1316.7 centimeter cube. So what I will do, this is the Zp required, this is the required Zp. So initially I will increase it by 20%. So approximately increase the section Zp by 20%. So what I will do, I will use this only, 1316.7 into 1.2. So let us check how much this works out. 1316.7 into 1.2. We are getting it as 1580.04 centimeter cube. So now I will go in the IS 800 2007 page number 138, wherein the properties of sectional properties are given for the plastic sections. So here it is. So I will keep it like this. So here it is. So here we will see Zp, plastic modulus Zp. We already have an answer. Our answer is working out to be 1580.04 centimeter cube. So anything above this, that section will be taken into consideration. So let us go on checking here what all we have. So you can check. So 1580. So 1580 is there. Above this is 1626, which the section is working out to be ISHB 400. But what we'll do, we'll take up on a higher section. So let us take 1760. So here it is ISWB 450. So I'll take that section. So from IS 800 2007 page 138, I will try a section based on this value. So anything above this in the Zp section. So I have chosen a section here which is having a value of 1760. So that is ISWB 450. So trying a section ISWB 450 at 79.4 kg per meter. Now remember, this section has to be chosen from the IS 800 itself. So we have chosen a section. Now let us note down its properties. Now for the properties you have to go in the steel table. So just let us check ISWB 450. So ISWB 450 is given here. So we will just note down the properties. So it is given here ISWB 450. So these are the section properties. Please note down it. So thickness of flange, thickness of web, breadth of the flange, this is taken as D, this total is taken as H. So let us note down. So H is 450 mm. Then from the table, so breadth of the flange is 200 mm. Then thickness of flange 15.4 mm. Thickness of web 9.2 mm. Okay, so I have noted down the, even I will note down the root radius. So root radius R1 is 14 mm. So these are the properties which has to be noted down. So I will continue this in the next part.